We have covered the charge voltage model of a MOSFET. However, it is not sufficient for circuit simulations, as the transcapacitance are also needed in the Jacobian matrix to evaluate the circuit equations. We have to derive the capacitances, which will be covered in this presentation. Let me remind you that the approach to handle nonlinear multi-terminal capacitors have been covered earlier in the 6th presentation in this series. I strongly encourage you to revise those material while going through the contents in this presentation. For a MOSFET represented by the symbol given here, there are usually capacitances associated with each terminal. For example, the most important one is the capacitance associated with the gate terminal, because it represents the loading contributed by this MOSFET. To represent the gate capacitance, capacitors like what is shown here in the figures is usually added. But we have to be very careful about the meanings of these capacitors. The capacitance, as observed from the gate, is usually written as CGG. A capacitor actually represents the change of charge with respect to a change of a voltage. So, the capacitor CXY is given by the partial derivatives dqx dvy, which we have explained in video 6 on nonlinear capacitors already. We can say that CXY represents the change of Qx with respect to the change of Vy. So, CGG is given by the change of the gate charge, Qg, with respect to the change of the gate voltage, Vg. In that case, what do three capacitors drawn in red represent? Let's take the capacitor between the gate and drain as an example. It may represent the change of part of the gate charge with respect to the change of Vd. In that case, we can write it as CGD. Or it can also represent the change of drain charge with respect to the change of gate voltage. In this case, we can write it as CDG. In a two-terminal capacitor, CDG is equal to CGD, as the charges on both sides of the capacitors are the same. It only depends on the voltage difference across the two terminals. However, it is not the case in a multi-terminal device, as the capacitances becomes transcapacitance. It is like transconductance in the IV model to represent resistance between any two terminals. In this situation, CGD may not be the same as CDG. So, in the given figure, can we say that the gate capacitance is equal to the sum of three individual capacitance as shown in the figure here? The answer is yes. Let's examine the gate charge Qg, which is given by the sum of Qd, Qs, and Qb, with opposite polarity due to the charge neutrality. So, CGG equal to dQg dVd, and it can be written as minus dQd dVg plus dQs dVg plus dQd dVg. Replacing the charge derivatives with capacitances, we have CGG equal to minus CDG plus CSG plus CBG. The negative sign on the right-hand side of the expressions requires some of the capacitance to be negative. However, negative capacitance is not a generally accepted concept. To eliminate the negative capacitances, the formal sign convention of the transcapacitance is given here. When X and Y are both referring to the same terminal, we consider the capacitance to be positive. That is, the terminal capacitance CXY are given by plus dQx dVy when X is equal to Y. But the sign will be assigned to be negative when X and Y are not referring to the same terminal. That is, the transcapacitance CXY is given by minus dQx dVy when X is not equal to Y. It makes sense because the charge stored in a terminal will usually decrease when the voltage of another terminal increases. With this convention, we can write the gate capacitance CGG as a sum of three capacitances as shown in the figure and given by the equation here. But what would happen if we switch the charge storing terminal and the contouring terminals with varying voltages of the three capacitors as shown in the figure? To analyze this, we note that the total charge stored in the terminal will not change if all voltages are varied by the same amount. That is, the sum of dQg dVg, dQg dVd, dQg dVs, and dQg dVb is 0. After replacing the partial derivatives with the corresponding capacitances and rearranging the terms, we have the value of CGG is also equal to CGD plus CGS plus CGB. Therefore, the total capacitance at the gate can be represented by the sum of three individual capacitors under the following two cases. The first one indicates the change of the gate charge with respect to the change of the other three terminals. The second one indicates the amount of charge change at the three terminals due to the change of the gate voltage. However, generally speaking, these capacitors are non-reciprocal. That is, CGD is not necessarily equal to CDG, and so on, in terms of both magnitude and sign. As there are four terminal charges and four terminal voltages, there will be a total of 16 capacitances to be calculated. Among them, there are 4 terminal capacitances and 12 transcapacitances. It is more complicated than the IV model because the transconductance will be 0 with an open circuit. However, most of these capacitances are non-zero. Fortunately, we do not need to calculate all 16 capacitances. It is because if you put all the capacitances into an array form, you will notice that for every row and column, there is some need to be all 0 as we derived earlier. It is also called the charge neutrality requirement. So, we only need to calculate 9 of the capacitances and the rest will be defined. I will not spend the time to derive the capacitances in this presentation, as all the charges has been given in the previous video. Deriving the capacitances by differentiating the charges is just a mechanical exercise. Once the capacitances are calculated, they are used to fill the Jacobian matrix during circuit simulation. For example, the matrix stem for the MOSFET charge model at the ith iteration point and kth iteration step is given here, assuming the trapezoidal rule is used for iteration. This expression is the same as the one given in video 6, but for a more specific device. The most difficult part in the formulation of the capacitance model is to match the physical data. The capacitances are not derived directly from the behavior of the capacitors, but through the differentiation of the charges calculated using the charge model. A small error in the charge model can lead to significant error in the magnitude and behavior of the capacitances. In particular, there are 16 capacitances, which means that the charge model needs to be accurate after differentiating with respect to all 4 node voltages. To ensure the capacitances are accurate, we have to understand the behavior of the capacitors. Here, we will qualitatively look at some examples. I will not cover all the capacitances, as it will be very time-consuming to do so. We first look at CGG. At small VD close to the source voltage, we can treat the source, drain, and body terminals as ground. When we measure the gate capacitance as a function of gate voltage, CGG is just the classical MOS capacitor given in many textbooks. When we apply a positive drain voltage VD, the capacitance below VT remains the same, as the charge is provided by the substrate terminal. That is, QG is just equal to QB, which is independent on VD. You may want to refer to the previous video for the corresponding charge-voltage relationship of a MOSFET. And CGG is just equal to CGB, while CGS and CGD are close to zero. When VG increases beyond VT, the MOSFET first enters the saturation region. Also, as mentioned in the previous video, the channel charge in the saturation region is only 2/3 of that in the linear region. Therefore, the capacitance becomes 2/3 of Cox. When VG is further increased to beyond the point VT plus VD, the MOSFET entered the linear region. Then the capacitance gradually returns to Cox after that. If we look at CGG as a function of the drain voltage, we note that at VD equal to 0, the MOSFET is in the linear region with the source and drain symmetrical to each other. In this case, CGG is just equal to Cox. When VD increases, the total gate charge is reduced, leading to a decrease in CGG. And finally, it will reach 2/3 of the initial value when VD becomes VD set. Then the CGG will stay constant, as shown in the figure here. At higher VG, VD set becomes larger, and it will take larger VD to reach 2/3 of Cox. The change of CGG with VD will become more gradual. Another important capacitance to look at is CGD, as together with CGS, they combine to form a major part of CGG when the MOSFET is turned on. We will study their characteristics together. Below VT, the gate charge is equal to the substrate charge, that the source and drain terminals are not making any contribution. So the drain and source voltages have no influence on the gate charge, and both CGD and CGS are close to 0. After VG becomes larger than VT, the MOSFET enters the saturation region. CGD and CGS are then depends on the charge partition model. If we refer to the charge equations given in the previous presentations, the gate charge is independent on the drain voltage after VD go beyond VD set. Therefore, CGD will remain to be 0. On the other hand, all gate charge is modulated by the source voltage relative to the gate terminal through the VGS term in the saturation region. Therefore, CGS will be 2/3 of Cox. When VG increases beyond VT plus VD, the MOSFET enters the linear region, and the differentiation between the source and drain becomes smaller. Eventually, they will both approach half Cox, as each terminal will contribute half of the gate charge in the linear region. When we look at CGD and CGS with respect to the drain voltage, they both start from half Cox at VD equal to 0, because the source and drain are symmetrical. When VD increases, the drain terminal is gradually cut off from the channel, and CGD will approach 0 when VD equal to VD set. CGS, on the other hand, pick up all the channel charge, and it will become 2/3 of Cox after entering the saturation region. When VGS is increased, the VD set is also increased. Therefore, the change of CGD and CGS with respect to VD is more gradual. Up to now, we have derived the QV equations and CV equations of a MOSFET independently from the IV equations. However, the charge equation is also needed when deriving the IV equations. When we derive the drain current of a MOSFET, we wrote the current at any location Y in the channel is equal to the charge density at that location times the velocity of the carriers at that location. In the derivation of the IV equation, an expression of charge in terms of voltages is required after the integration over the channel region. Ideally, the charge used in the IV equations and the charge used in the CV equations should be the same. But it is in general very difficult, as they have to fit different set of curves that are derived independently from each other. For example, many fitting parameters are added to various terms in the IV model to improve its accuracy. These parameters will also have different implications to the charge terms used in the IV equation. But in most cases, these modifications are not incorporated in the QV and CV models. As a result, inconsistent charge equations are used in the IV model, QV model, and CV model. That is, the Qs used in the IV model are different from the Qs used in the QV and CV model in circuit simulation. What potential problems will such model inconsistency cause? It actually depends on the purpose of the simulation. It will not cause any problem in DC or transfer function simulation. It is okay, as the QV and CV models are not used. In transient simulation, the IV model and QV model are calculated separately to generate entries into the Jacobian matrix. It will not cause any simulation issues, but just the beauty of the physics may be sacrificed. That is, the model may be considered to be more empirical in nature. In some sense, you may also say that the physical accuracy of the model is compromised. In terms of simulation results, circuit designers usually concern about the time delay, and is more tolerable to the shape of the rising and falling edge details of the circuit output. In that case, the IV detail is more important than the physics of the QV and CV characteristics. In AC simulation, the biasing point is first determined. It only requires the IV model in the setup. After that, the current and charge derivatives of the model are linearized. As a result, the exact physics of the CV model is again less important in the process. Given this general usage of model in circuit simulation, the IV model is more important than the QV and CV model. It becomes also a common practice that no consideration is put to the QV and CV models when improving the IV model. For example, new parameters added to adjust the charge term in the IV model will not be applied to the QV and CV models. This approach is not ideal, but in general acceptable to reduce the complexity of developing a model to a manageable scale.